Lanissa? That's right. Okay. Every time, it's just like it's spelled. All right. What do you think of that?
Did you say earlier how it should be bounded?
Pardon?
Earlier you said it was bounded.
Bounded. So this is, so can you're visualizing what this looks like, right? So you're imagining the sine function, right? Going like that. And we're heading out to infinity, and I'm asking you, just look at that function, tell me what this thing is approaching as I keep going. So is it approaching something? Well, x is approaching infinity, but is the y value approaching something? Is the function approaching something? No, it keeps oscillating, right? Here we don't have, on the bottom we don't have something getting big, right? So we don't have like bounded over infinity, we just have bounded, right? But it's doing this. So this limit does not exist. It's not headed to one place, is it? It's not headed to one place. Okay? What about this one? I really have always liked this sort of problem. X goes to infinity. Square root of x minus x. We'll start out with that one. What does your instinct tell you, Luke? Luke? Where's Luke? Okay. What is your gut telling you anything on that? Okay, it's infinity minus infinity. But when you look at those two functions, I should say this, Luke, infinity minus infinity is not 0, right? That we have to get squared away, everyone. Infinity minus infinity is not 0. Infinity plus infinity is infinity, all right? In fact, infinity minus infinity is on your sheet, isn't it? Do you see it? It's one of these things we don't know. 0 over 0, we don't know. Infinity over infinity, we don't know. Infinity minus infinity, we don't know. We have to do something. So here, if you look at this one's becoming infinite, right? Minus this one's becoming infinite. Do you have just a gut instinct on which of these dominates the other?
The one without the square root?
Yeah, just the x by itself should be getting bigger faster, right? This one should be getting bigger faster than that one. So this subtraction of this one should dominate the other one. But that's not good enough. We need some algebra to do this. So how about, I'll let Luke off the hook. I would like anyone here to factor square root of x minus x. Can you factor GCF, greatest common factor? What do they both have a common factor in them? Maybe I can help. Okay. What's the common factor? X to the 1/2. X to the 1/2. Well, let's think about that. If you pull an x to the 1/2 out, you have to get back this, right? So what's the first term here? 1. Minus, now what do you need here to get back x to the first power? X to the 1/2 again, right? Because when you multiply these and they have the same base, you add the exponents. 1/2 plus 1/2 is 1, right? But this is the same as doing this. Limit x goes to infinity, square root of x times 1 minus square root of x. That's the same thing, right? So we could have like pulled the square root of x out. If you like to look at it that way, you could pull the square root of x out at the beginning. Now, Marissa, why does that help? Now we have multiplication. Okay, we have multiplication right here. So Marissa, when you do this, where is this one headed? The square root of infinity, infinite, okay, times, now here you have 1 take away infinity, right? So this is going to be negative, right? This is going to be a negative infinity. So you have infinity, and you're multiplying by something that's becoming huge but negative. And we know infinity times infinity should be infinity, right? But if one of them is positive and the other one's negative, we should get negative. So this should be negative infinity. Do you all follow that? Positive infinity. One take away infinity is going to be negative infinity. Multiplication of a positive and negative give you negative. So it's like Luke's instinct was right. This one seems to dominate this one, so we should be heading to negative infinity. One more of these. Dun, dun, dun. Elijah? Had time to write it down and look at it for a moment? I didn't call on you already? Didn't you already respond to something? No? Okay. All right, so let's just see what's happening, right? X is going to infinity, so infinity squared, infinity. Cube root of infinity still should be a big number, right? Okay, so that's headed to infinity. Minus infinity to the 5th power, right? Still infinite, but then 4th root, which is still infinite. And Elijah, what's infinity minus infinity?
Not zero.
Not zero, good, thank you. Not zero. So what have we been doing when we've seen infinity minus infinity? This is I believe the 3rd time we've seen it. The first time we saw it was with Danielle in the middle of a problem. We were looking at 4x squared, I think, minus x. Remember that? And then what did we do when we had that back with Danielle? We did it over there on the side. We took an x out, we factored it, right? And then what we just did was square root of x minus x, right? And that was infinity minus infinity. What did we do with that? We pulled a root x out, so we factored, right? So the rule of thumb on these, and it's not always true, but when you see infinity minus infinity, a lot of times you want to be thinking factor. Won't always be that way, but it's something to try. So when you look at this, of course, it's obvious what to pull out of this, right? Yeah. That's not as easy to factor, is it? But we can do it. Okay, so let's just go on the side and do some scratch work real quick. Let me get through these. Jackson, you've already, good? You want to go? All I want, Jackson, here is if you can rewrite this using rational exponents instead of...
Yeah, it'd be x to the 2/3.
2/3? 5/4. Okay, so just remember, everyone, whatever power is in here is the numerator, whatever the root is the denominator. All right? Any ideas, Jackson, on how to go about that? If I'm going to try and factor something out. This is a little tricky. If you've never done it, it's a little tricky. It's not terrible. Yeah, okay, so let's do something with the exponents. Let's do something with them.
Maybe like a subtraction or something. Like kind of taking the 5/4 and breaking it into like maybe.
Like, it'd be real nice if like there was a 2/3 in there or something,
Yeah.
right? What would be even better is if they both had like the same denominators, right? So could you rewrite this as a fraction that would have the same denominator as this one? Or maybe you can rewrite them like at the same time, like rewrite both of them. So Jackson, what's a common denominator that you would have between those two?
12.
12. Okay, so how can you rewrite the first one as something over 12?
8/12.
8/12. minus, and then this one right here you can rewrite as 15/12. Everyone see that? Now, what do they have in common? Well, they definitely have an x to the 12th. I mean, sorry, not x to the 12th. That's not what I meant to say. Let's see if y'all agree with this. I could definitely pull out a 1/12 like that. Okay, now don't write this down, but do you agree I could do this? So what would be here if I just did this? X to the 7/12 minus x to the 14/12. Now, I said don't write this down. The reason why is because when we multiply these two together, we add them up, right? And we get 8/12. Go here, add together, we get our 15/12, right? But do you see that this doesn't help? Like this doesn't save us? Because this is infinity, right? But what's this? Infinity minus infinity. So, gosh, maybe there's something else I can do. Like 1/12 wasn't enough. Yeah, 8/12. Because this one's 8/12, that one's 15/12. So just pull the whole 8/12 out. And what will that turn the first one into? 1, and then minus, the second one will be x to the 7/12, and now we have it. Okay, because this is infinity raised to that, right? Yes? So this is like the infinity to the 8th power, take the 12th root, which is still infinity. Times, though, and then this is 1 take away infinity to the 7th power, take the 12th root. So this is like 1 minus infinity, which is negative infinity. And now we have infinity times negative infinity, which heads to negative infinity. All right, see how that works? So from radicals to rational exponents to common denominator rational exponents, pull out the smaller of the two, and then you should be in business. Okay, how about this one? What are we doing here? 20. Change it up just a little bit. X is going to go to negative infinity this time. Anybody miss pre-cal yet, or we're okay? David, didn't I call on David? No, there was 2. So you're good. You've done yours, and so that's all right. We just, I might have called you earlier. Let me see. Wait, was it your name? Is that your handwriting? Yes. Here. Yes. No. Yeah. Go ahead and just put M on the end of that. Yeah. Okay. All right, so you're up then. So where's x headed to? Negative infinity. So out to the left, right? That changes a lot of things here, all right? It's still getting big, but it's getting big negative, right? So let me start with this, David. This right here. What is that doing as x goes to negative infinity? What is the cosine function doing? Like that? Like that? So we're doing that, right? So we're doing a cosine function out that way. So this thing is just oscillating. It's not fixed, but it's definitely bounded, right? So we know that this is bounded. Now, this is the tricky one, right here. So do you have an idea what e to the x looks like in your mind? Which way are we headed? Where's x headed?
What's negative?
Negative infinity. That's right. So negative infinity is this way, right? So what is e to the x doing as you go that way?
It's getting smaller.
Where's it headed? Smaller to 0, right? It's headed towards 0, right, everyone? This one is headed towards 0. Just look at the graph. Here's e to the x. But see, we're headed to negative infinity this time. So we have that horizontal asymptote. If this was headed to positive infinity, then we would be going that way and going up, and that would be going to infinity. Okay, so that little subtle change made a big difference on this one, right? Really wouldn't have made a difference here. Cosine's going to oscillate no matter which way you go. So what do we get whenever we have 0 over bounded? Do we have anything on here for 0? I mean, I said 0 over bounded. That's not what I meant to say. 0 times bounded. I don't see anything on here that says 0 times bounded, do I? Okay. So what do you think the answer is going to be? You got a number that's getting really, really, really small times a number that's bounded. You think it'll get bigger? Think it'll get small? So let me try and help you settle the score here. We'll see if we can't determine this. How about this? Is that the same problem? That's the same problem, isn't it? Because all I did was I moved the e to the x down and made e to the negative x. That's just me using some algebra. Drop it down, right? The exponent changes. Now let's run through it again. Right, David? X goes negative infinity. We know that that's bounded, right? So that on top is bounded. Now on the bottom, David, if I take x, let it become really big and negative, and I plug it in right here, then I'm going to have a big negative number times a negative number, which would become positive, right? And then that means e to the positive infinity would become infinitely big, right? So this would become infinite, which is going to give us 0. Because that we already established. Bounded over infinity is 0. So bounded over infinity always gives us 0. But we had to kind of mess with this e to kind of really see it. I hope that that kind of helps.
How'd you get the infinity to the bottom?
Okay, so let's, yeah, this is important. All right, so let's just take a little bit of time on it. Let's imagine a number line, right? Here's 0. So we're going to let x head to negative infinity, right? So let's just imagine a very big negative number, negative 1,000, okay? What if x was at negative 1,000? You plug negative 1,000 in right here. Wouldn't you get e to the negative 1,000? Which is really e to the positive 1,000. And e to the positive 1,000 is like e, go out to 1,000, go up. That's huge, isn't it? So what happens is the fact that you have a negative being plugged in next to the minus becomes, this becomes e to the positive infinity, which,
But if it was positive, just
if this was positive, then this would go to 0. Yeah, because now you're going the other way on e. That's what I was trying to get you to see here. You'll need a little time to let that kind of sink in. Just make sure there's nothing else there that I want to do. Yeah, I think you're good for 1.6. You should be able to handle all the homework. Now we skipped 1.5. Remember that? I said I'd come back to it because it was a detour. We only have about 12 minutes, but I can at least get the idea across of continuity. So I'll do like the true formal like presentation of this next time. But I think I can get through a lot of it without having to, well, yeah. Continuity. Continuity. So I'm going to draw you some pictures. We're going to go back to pictures for a moment. Take a look at this function. And let's just call this point right here, let's call that A. Yosef? I'm going to underline you. Yusuf. Okay. Going back to limits. Does the limit of this function exist from the left? From the left. Do we have a left-hand limit here? So as you move, as we approach A, I should say that. As we approach A, from the left, is our function headed to something?
Yes.
Okay, so you're unsure, okay?
It's an open circle.
It is headed to something. Now at A, remember when we talk about limits, we don't care what's happening at A, right? So from the left, we do have a limit. Do we have a limit from the right? Are they the same? No. So does the limit exist at A? Is the function defined at A?
Well, yes.
Yes,
Close that.
because there's a closed dot there. Okay, so let's run through this again. Does the left-hand limit exist?
Yes.
Does the right-hand limit exist?
Yes.
Does the limit at A exist? No. Is it defined at A? Yes. Okay. How about this one? Left-hand limit exist at A? Yes. Right-hand limit exist at A? Limit exist at A? No. Defined at A? Yes. Okay, so these are pretty much the same answers for both of these, right? You get the same answer for both? Okay. Left-hand limit exist?
Yes.
Right-hand limit exist?
Yes.
Limit exist?
Yes.
Yes. Going to the same place. Function defined at A?
Yes.
Okay. Can you draw it without picking your pencil up?
No.
No. Now, I didn't ask that about these, did I? Let's go back and think about it again. Left-hand limit, yes. Right-hand limit, yes. Limit, no. Defined, yes. Can I draw it without picking up my pencil? No. Okay. Left, yes. Right, yes. Limit, no. Defined, yes. Can't draw it without picking up my pencil. Left, yes. Right, yes. Limit, yes. Still can't draw it without picking up my pencil. So what would I need? I would need, to draw without picking up my pencil, I would need what? Left exist, right exist, and defined, right? A dot, but that dot would have to be where? At the limit. Okay? Now I could draw this without picking up my pencil. This is the idea of continuous. Continuous. You can continually draw it without picking up your pencil. It's a very simple idea, right, in terms of just drawing something without picking up your pencil. But we're going to define continuity by using the limits, right? So let me show you what the definition of continuity is. A function is said to be continuous at x equals a if if, maybe you can tell me, what did we need for us to be able to say that this thing was continuous right here? We needed that the left and right hand limits were the same, right? So that means the limit at A had to exist, right? So we will say it's continuous at A if the limit as x approaches A of the function exists, right? But it existed here too, right? But what's the big difference between these two? Yeah, the value of the function, right, here at A had to match up with the limit, didn't it? The value of the function here doesn't match with the limit. So how do I say that right here? I need this limit to match the function's value. I need the limit from the left and the right has to exist. And it has to be equal to the function's value. So this is the dot, this is coming in from both sides. And they have to go to the same place. That's what that definition means. So So there it is. That is the definition of continuity of a function at a point. Simple enough? Types of discontinuities. All right, so before I put this up here, we only have 5 minutes left. I'm going to pass the sign-in sheet around. We may be way off on this. Let me see. Today's the 10th. So go quick with this because we only have 5 minutes. Don't put this right here because it's a separate idea. If I draw a nice little polynomial function, right? Nice good old college algebra polynomial function. Is this thing continuous right there? Yes, because from the left and right you had the same place, fill it in, right? Everything's good. Is it continuous there? Yes. Is it continuous there? Yes. There? Right. Polynomial functions are continuous everywhere, right? Sine function. Continuous, cosine, right? Okay, so we're not really interested right at this particular moment about talking about continuity and continuous. What about, like, where would we ever have problems, like discontinuous? So what about this right here? If we ever have this situation, that would definitely be discontinuous. Why is that discontinuous? Which of these fails to work? The limit doesn't exist, right? Right? That would fail. This left side would be does not exist. So this right here, we call this a jump discontinuity. Anywhere you have a graph that all of a sudden jumps, breaks apart, that's called a jump discontinuity. All right? Where else would we have a discontinuity? What about this? So that's one. Okay. How about this one? And I don't even need to put the dot here. Right there, does this limit exist? Does the limit exist? Yes. Is it equal to the function's value at that point? No, because the function isn't even defined, right? This is called a hole or a removable discontinuity. They call it removable. The reason they call it removable is because it would be very easy to fix. What would be the one thing we would have to do to fix this problem? Just close the hole up, right? We could easily plug that. This one you can't fix because you would have to completely redefine the function and move that piece together, right? And then we could fix it, but that's too much work. This one, just fill it in. Can anyone think of anything else where we might have any type of discontinuity? Asymptote? What kind? Yeah, like what if we have a vertical asymptote? So what if we're sitting there back in college algebra trying to draw a rational function and we have to do something like this, you know, like that, and we got this. Can you draw that without picking up your pencil? No, right? So you have infinite discontinuities. And those are the three types. Good job. So the three types of discontinuities that we'll deal with here in this class are jumps, removables or holes, and infinite discontinuities. So that gives you kind of a geometric idea of what continuity is. Next class we'll actually go back to that limit definition and we'll start doing some problems and work into that topic a little bit more. Do your homework. Yeah, we meet again on, I'm losing track of days. Today's Tuesday. Just as you're packing up, Thursday I'm going to have limited availability. before class. I will be here probably around noon, but I've got a commitment in the morning. I just want everyone to know that. So I'm in my office usually at 9:15. I won't be there till probably about noon on Thursday. And then I won't be here Friday, and I won't be here Monday. So just so everyone knows, all right? I'll be out. But I will be here Tuesday, ready to go. All right, have a great day. Do your homework.
Like say, like, I mean, I for sure I would love
Was it? Yes, sign it. Anyone else need to sign in? Yes. Okay. Yes, what's up?
The main things to remember right now is these three and the junk formula. So like you said, burn them over my head, just always remember.
Well, we don't have all of these yet.
Okay.
We only have 0, 0, infinity over infinity, infinity minus infinity. We have not talked about that one, that one, that one, that one.
Okay.
And then yes, know this, know that. And then this one, this is just an obvious one. Like anytime we get 0 on top and a number on the bottom, the answer is 0. So like if you take the limit on top, you get 0, on the bottom you get 5, the answer is 0.
Okay.
Okay, so that one's, there's no trickiness to it, it's just you get an answer.
And then the junk formula. As well.
The junk, yep.
For sine, cosine.
For sine, yep. Remember that, yep. Okay.
So
Yes, sir.
I have a question about
Yep.
infinity. So
Yes.
like or perhaps it's not specifically infinity, but I mean, what happens when you have like limit of like x as x approaches infinity?
You want to write something down for me? Yeah. Go
Yeah,
ahead.
the one-
Oh, there you are. Okay. Yeah, go ahead and write something down. All done?
I
Okay.
think so. Except David didn't sign it.
Okay.
Oh, yeah.
Yeah, I'll make sure he signs. Very good. Get your stuff.
So what if you have something like this? Like how would you solve it?
Well, these aren't equations. What this would be saying is that as we take a look at this function, as we draw it and we move out to the right, we're saying that the function is taken off to infinity.
Okay.
So this is not an equation to solve. I mean, if you were asking me to come up with a function that behaved like this, then I could just give you the function e to the x. I could also give you the function x squared. Like if you graph that, it goes like that. Graph this, goes like this, right? So both of these, as you go to the right, as x goes to infinity, the function starts to go to positive infinity, right?
And that, sorry, I guess, sorry, I think I did the notation wrong. So I mean,
Okay.
what if you did limit x as x approaches infinity, then it's infinity. Would that just then be like that, or
I'm not understanding the question.
so
Are you
it
saying
wasn't?
like as x goes this way, it just goes infinitely higher?
Yeah. Is
So
that
it's just like an exponential function.
okay?
Anytime you take a limit as x goes to infinity and get infinity as an answer, what you're saying is that whatever function you're talking about, as you go that way, it goes up forever.
Okay.
That's what that would mean.
Okay.
That the function itself, I forgot to turn the camera off. The function itself could be a lot of different things. Not every function